I'm David Sloan. I work on the fine-tuning project here in Oxford, and today my guest is Robert Brandenberger of McGill University, who's going to talk to us about fine-tuning issues and inflationary cosmology. Welcome.
Thank you. So thank you for the invitation to participate in this big event. So I'm very happy to actually be here in an event on inflation, because I've seen inflation develop from a wild idea to something which astronomers now consider to be the paradigm of early universe cosmology. So if we go to a talk given by astronomers and astrophysicists, they will start off their talk saying the universe began with a period of inflation. And I guess we will discuss whether we really know whether this is true. Mm-hmm. But let me give an introduction which will also address the issue of fine-tuning a little bit. So the way that I encountered inflation is when I was a graduate student at Harvard, and a friend of mine, Jenny Trashen, came up to me one spring and said, why don't we do something special over the summer, something which no one with a PhD knows about. This was the birth of a secret student seminar, and Jenny had found a paper by an unknown physicist by the name of Alan Guths. This was in the prehistoric time of preprints, long before the archive, before the internet. So there was this paper which had the title The Inflationary Universe, and over the summer we taught ourselves the material to understand this paper. So this was a paper proposing that the universe almost started, because it didn't quite start. There was a pre-inflationary phase, but quite early to the origin of time. And by quite early, I mean 10 to the minus 30 seconds after the Big Bang. The postulate was that there was a period of exponential or almost exponential expansion of space. And then in the years afterwards, it was realized in the West that with this theory, we could make predictions for structure in the universe, anisotropies in the microwave background, and structure of galaxies. And I should mention that at that point, structure of galaxies was known. So it was, in a certain sense, a consistency check on this new theory, that it was consistent with what we knew about the structure of galaxies. But although the microwave background had been discovered, no anisotropies had been measured. But this wild idea of exponential expansion of space, it predicted a particular pattern in anisotropies in the microwave background. And these anisotropies in the microwave background were then discovered in, I think, 1992, which was more than 10 years after the invention of this theory of inflation. And it was mapped out with high precision 10 years after that. So 20 years after the proposal of the theory.
So you called this a wild idea. Why was it considered wild?
Okay, so at that time, 1980, in the West, there was a disconnect between particle physics and general relativity. Particle physicists never learned general relativity, and general relativists never bothered about particle physics. The fields were almost separate, and none of them were really connected with astronomy. And so here was a particle physicist coming up with an idea based on quantum field theory, which had some implications for general relativity and cosmology. So it was really showing a new direction. So that's why I call it a wild idea.
Okay. And so what sort of motivated Guths to do this?
Okay, so Alan Guths was motivated by fine-tuning problems of standard Big Bang cosmology. And standard Big Bang cosmology is what you get if you assume that the universe is homogeneous and isotropic. It's the same in all directions, same everywhere in space. And that the matter that causes the universe to expand is simply a gas of point particles and radiation. So this standard Big Bang cosmology had fine-tuning problems if we wanted to explain why the universe is so big, why the universe is homogeneous, and why it is spatially flat, to the extent that we can measure deviations from spatial flatness. So there were these fine-tuning problems, enormous fine-tuning problems. We're talking about fine-tunings to the level of 10 to the minus 38, 1 part in 10 to the 38. So extreme fine-tunings. And this, with this idea of inflation, these fine-tuning problems disappear, to be maybe replaced by other fine-tunings, but that's for later.
Okay. So when you say that these fine-tuning problems are alleviated, sort of, could you expound on, for example, how does this answer questions of the horizon or the flatness of thermalization?
Right. Okay, so one of the problems of standard Big Bang cosmology is that it cannot explain the fact that the microwave background has the same temperature in opposite directions in the sky. So the microwave background is released, it's produced a couple 100,000 years after the Big Bang. Now the universe is 13 billion years. And so if we ask, in standard Big Bang cosmology, is it possible to explain causally that regions that we now see in opposite directions in the sky have the same temperature? You find that it is not possible. The maximal region in the sky that could have been in causal contact is something of diameter of about 1 degree, not 180 degrees.
Right.
So even though the standard Big Bang cosmology explained the origin and black body nature of the microwave background, a major success, it did not explain the fact that the temperature is isotropic. So the major success of standard Big Bang cosmology had built in it its downfall, the downfall of the theory. So that's one fine-tuning. The other fine-tuning is spatial flatness. So to the accuracy that we can measure, Euclidean geometry applies to space. There are no deviations from Euclidean geometry. So our space is not the three-dimensional equivalent of the surface of a sphere, but it's a three-dimensional equivalent to the surface of a flat table. So now if you look at how spatial flatness evolves in an expanding universe, you find that the smallest amount of spatial curvature in the early universe amplifies relative to the energy density in standard matter. So that's a spatial flatness problem. And again, if we imagine that the universe was born at a temperature which has energy of about 10 to the 16 GeV, so typical energies of particle physics ground unification, then we again have a fine-tuning problem of about 10 to the minus 38. Now the way that inflation alleviates that is that during the period of exponential expansion, spatial flatness is achieved at an exponential rate. So if at the beginning of inflation you start out with equal amount of spatial curvature and matter, that when I say equal amount, that's in terms of energy units, then the strange matter that inflation postulates, it is constant in time, whereas the energy in spatial curvature decreases exponentially. So this is a way that you can achieve the exponentially small energy density in spatial curvature that you need once the universe starts to expand as described by standard Big Bang cosmology.
So this sort of brings us naturally into questions about the matter models that one introduces to cause this effect and the geometry of the expansion itself. So everything you're talking about so far really requires this exponential sort of de Sitter phase of the universe on the one hand. And that seems to be what you're saying is actually answering the fine-tuning questions.
Right.
Whereas on the other hand, what you're having to posit is this new form of matter somehow that is causing this effect. You know, you put this into the Friedmann equation and this gives you this.
Absolutely.
And you say it has to behave a bit like a cosmological constant.
Right. Now, the beauty of this original paper by Alan Guths was that this seemed to emerge naturally from quantum field theory and particle physics. So what Alan Guths imagined is that you have a field a little bit like the Higgs field. So at that point, the Higgs particle had not been discovered. But most particle physicists were convinced that there is a Higgs particle and there's an associated Higgs field. And this Higgs field has a particular potential energy function, which it needs to have for it to give particles masses. And the potential is a little bit like a Mexican hat potential. So the field is a two-dimensional field, and the space of minimum energy field configurations is a little bit like the trow in the Mexican hat. But then the center point in field space, it's a little bit like the tip of the Mexican hat, and that has positive potential energy. And potential energy, if there is only potential energy, it leads to exponential expansion of space. It has the equation of state, like that of a cosmological constant. So Alan Guths imagined that there are thermal effects that put this scalar field at the top of this potential, at the center of the Mexican hat. Alan Guths imagined that thermal effects would stabilize the field there for some amount of time, and that then some well-understood quantum field effects would happen, and the field would evolve to the bottom of the potential where it is now. So the idea seemed to emerge naturally from quantum field theory, and that's why immediately many quantum field theorists paid attention to this inflationary idea. Now, Alan Guths also realized that this initial idea did not work. So we now call Alan Guths' model of inflation, we call it old inflation. So old inflation because it didn't work. So again, Alan Guths realized in this paper that this idea needed more work, that the form that he proposed, it did not achieve its goals. The problem is that now, 37 years later, we are still trying to make inflation work from the point of view of fundamental physics. So we still have not achieved the goal. And this statement that I'm making now is a statement that not all particle physicists and field theorists would sign.
Right. And so, on one hand, you're saying that we had this natural model that arose from quantum field theory. You should think of this scalar field with this Mexican hat potential as being sort of the natural thing you would expect to be to explain inflation, to play the role of the matter model. And this was introduced to solve some fine-tuning problems. But then you say that, okay, this old inflation doesn't answer these questions because it doesn't agree with observations and so forth.
No, it's not that.
Okay.
It's not that it doesn't agree with observations, but this old idea doesn't produce a large universe like the one that we see today. So it's actually the mechanism of inflation which didn't work. So there was an idea of how you could get inflation, but that particular model did not produce a large universe that has exited inflation. So it's not a question of the model not agreeing with observations. If the model had worked to give a large universe, it would have worked. So the problem is not comparing with observations, but it's at the fundamental level.
Okay, so let me perhaps rephrase that. This old inflationary model did not do the job that it was posited to do originally. And so one has to introduce newer models. And of course, there's a whole plethora of these, I think.
It was immediately replaced by something called new inflation.
Right.
So, and the people responsible for that were Andre Linde and Andy Albrecht and Paul Steinhardt. So just to get the timelines, to set the timeline, Alan Guths' paper on inflation was published in 1981. The papers on new inflation, 1982. But just to get the history right, there was a prehistory of inflation. For example, Alexei Starobinski, behind the Iron Curtain at that point, had an inflationary model back in 1978, and there were some precursor models by Katsuhiko Sato in Japan, by Feng Liji in China, and by various other people.
Well, it's interesting you mentioned the Starobinski model in particular, right? Because this doesn't actually seem to use the same mechanism. One doesn't alter the matter content, but rather the gravitational theory. So would this be a more natural explanation of inflation, in your opinion, or would this also suffer from issues of fine-tuning?
So I hesitate to answer that question now. So this model, the Starobinski model, came from general relativity. Again, I mentioned that at that point there was a disconnect between particle physics and general relativity. So Alan Guth came from a particle physics background. So he hardly knew about general relativity, but he certainly did not want to modify general relativity. So he basically just took general relativity, and as matter content he put in something that particle physicists would like. Whereas Starobinski came from a background of general relativity. He'd even thought about quantum effects in general relativity, and he knew that if you want to merge quantum theory with general relativity, you can't use the Einstein action. You have to go beyond it. And so he wrote down a model, a simple model that goes beyond Einstein theory, and then he found that you get exponential expansion of space with that model. So from a point of view of quantum gravity, that model is not safe because other corrections are not under control. So in that sense, it is not more natural. It also did not do the job because it also did not give a correct connection with the late time cosmology that we observe. So neither Alan Guth's original model nor Starobinski's model made a successful connection to late time cosmology.
So when we talk about late time cosmology, we're talking about a universe that's undergone a period of exponential expansion in which this inflationary field or whatever corrections to gravity caused this almost de Sitter phase. The universe then went through radiation and matter domination. But we're now in an exponentially expanding phase again, in which we sort of invoke the cosmological constant as an explanation for. Is there any connection between the early inflationary phase of this exponential expansion and the one we currently observe then?
Okay, let me go back to the first part, what you said. So when I say standard cosmology, I mean the cosmology that we can probe, and we had probed in 1980 with observations. So we know that the standard Big Bang cosmology picture applies today. It applied when the microwave background was released. It applied when the abundances of like elements were generated, so time of nuclear synthesis, and maybe a little bit further back. So that's what I mean by standard Big Bang cosmology. So any theory of the early universe has to connect with this standard picture, at least at the time of nuclear synthesis. Because that's addressing the first part of what you said. It's actually very different from the second part.
Right.
The second part is now the dark energy. So we see that the universe is accelerating now. It has recently started to accelerate. And you're asking the question, could the acceleration during inflation be connected with the acceleration that we see today?
Yes.
So this is a very interesting question, and there are different answers to that, depending on how radical you are in terms of fundamental physics. So the first answer that you would give is absolutely not. They are totally unrelated, because what determines the acceleration now is physics of very low energies, whereas what determines the initial acceleration, if there was initial acceleration, is physics of very high energies. Now, you can write down toy models of scalar fields. So scalar fields is a toy model of particle physicists. And for people who are not familiar with scalar fields are much simpler than electromagnetic fields, which everyone is familiar with. So scalar fields are much simpler. And up to the discovery of the Higgs particle, no one had ever seen a particle in nature that is described as scalar field. But anyway, scalar fields give you lots of freedom to do things. And with a scalar field, you certainly can construct a model which has both inflation and dark energy in it. You can construct it, and you learn absolutely nothing by doing that. Absolutely nothing. So it's not worth doing that.
Right.
Okay. So now, if you want to get acceleration today and acceleration in the early universe from the same physics, then you have to dig a little bit deeper. Then you have to ask, is there evidence in nature that there is something that connects the infrared, the low energy, with the ultraviolet, the high energy? And there is something. And now I want experts not to listen. Experts are not to listen because I don't want them to develop this idea. Okay? So in superstring theory, there is an infrared ultraviolet correspondence, which has not really been applied to cosmology at all. So if you want to use new fundamental physics, the answer may very well be yes. But this has not been worked out. Okay. So it's a long answer to something that sounded like a very simple question.
Well, those are the best answers in general.